Hello everyone. So we were discussing the dislocation dynamics at high strain rate. So we have discussed thermally activated dislocation motion and drag controlled dislocation motion. Now we will talk about the third mechanism, that is relativistic effects on dislocation motion. So this is the third one. Relativistic effects on dislocation motion. So very quickly we will draw this diagram, whatever I have drawn probably a couple of times. This is resolved shear stress, that is the applied stress, and this is dislocation velocity. We are keeping it as small v in meter per second. So for the nickel, so it shows like three part here, the part 1, part 2 and part 3 from this point onwards, and as we can see that this has a limiting value. So this is Vs, that is the elastic shear wave velocity. So in the region 3, so we are talking about the region 3. So region 3, the relativistic effects will be dominant here. So what happens is the dislocation velocity small v approaches Vs, this is capital V, so that is as you know elastic, that is elastic shear wave velocity. So that will approach Vs at a higher stress, so that at very high actually stress, that is applied stress, or here we are showing resolved shear stress. So this relativistic effect is with the help of another plot we can show that. This is another plot. So the velocity of dislocation small v divided by capital Vs is in the x-axis, and then ut by u naught, I'll tell you what is that. This is in the y-axis. So ut here is total energy of a moving dislocation, energy of a moving dislocation, and u naught is the energy of a dislocation at rest, or energy of, we can write, stationary dislocation. So what happens if we plot it? So let's say we have here the limit is 1, so that means when dislocation velocity approaches the shear wave velocity, and here let's say our ratios are 2, 4, 6, 8, 10, like this, and then what will happen is, so this will rise and it will rise kind of to infinity. So this is the energy, the ratio of energy, total energy of a movable dislocation divided by the energy of a stationary dislocation, which is lower. If you see that it first start with from 1, because that means that the total energy of the dislocation is at rest, and that is both ut equal to u naught here. And so what the plot says is, the plot says if you take a limit from dislocation velocity v to Vs, if it approaches elastic shear wave velocity, then the total energy of a moving dislocation is infinity. It tends to infinity. If you see Einstein's relativity theory, so that says that mass at a velocity v, at a velocity small v, is related to a mass at rest. So here this mass is, or you would write mass at rest. So here this mass at rest is, we can call m naught, and here it is m. So I would better write a mass. So this will be is equal to m naught plus 1 minus v both square, v square minus c square. So as you know that c is the velocity of light. So if the velocity of the mass is approaches the velocity of light, the mass m will be kind of infinity. So that's the Einstein relativity theory. So very analogous. This is our dislocation velocity is also analogous to it. So here we can call that so analogous, that means what we are saying for dislocation. So what is that is, this is m naught 1 minus small v dislocation velocity divided by capital V s square, the elastic shear wave velocity square of that. So here m is equivalent or effective mass of the dislocation. Okay. So this is analogous. So that's why we call this a relativistic effect. So this is known as relativistic effects on dislocation motion. So as we know that we haven't discussed much, but just to let you know that dislocation, particularly the screw dislocation, generate shear stress. And these shear stresses and even it will produce the shear strain. So these shear stresses and strains cannot propagate faster than shear wave velocity, elastic shear wave velocity. So it is kind of sound or sonic barrier. So we can call this in bracket sound, that is called sonic barrier. I think you probably have heard about this. So what happens, the sonic barrier means the sudden increase of aerodynamic drag and other effects if an object for example an aircraft, okay, so approaches sound speed. So if yeah, if the actually velocity of if the velocity of object approaches the sound speed. So like for this screw dislocation, so we can say that this is sonic barrier for a screw dislocation is Vs, like what we had for a ordinary sonic barrier is the sound wave velocity is, let's say, c. So here we are saying that for a screw dislocation the limiting velocity is Vs, the elastic shear wave velocity. However, for edge dislocation, so we have both shear stress and normal stress. So edge dislocation generates both shear stress and normal stress. So the limit of this dislocation velocity should be Vs for shear stress and Vl, which is velocity of elastic longitudinal wave, or I would write elastic longitudinal wave velocity. So probably edge dislocation has two sonic barriers. So two sonic barriers, right? So first maybe first one is, let's say it may be first Vs and then Vl, as we know that the Vl is longitudinal wave velocity is higher than Vs. The longitudinal wave velocity is probably 2 times that of sound wave velocity. It is believed that there are two sonic barriers for edge dislocation. However, it is not known that whether edge dislocation crosses velocity higher than Vs. That is not well established, but still it is believed to have two sonic barriers. One is at shear wave velocity for shear stresses, and for normal stresses it is Vl, that is longitudinal wave velocity. Velocity of dislocations were defined by Whitman, defined as small v, that is velocity of dislocation. I would write small v here as well. So that is if it is smaller than shear wave velocity, that is called subsonic dislocation, and if this is higher than shear wave velocity but lower than the longitudinal wave velocity, so then it can be called as transonic dislocation. And if dislocation velocity is higher than Vl, then we can call as supersonic dislocation. So the famous researcher SLV in 1956 proposed that supersonic screw dislocations are available. However, these supersonic dislocations are known as SLV dislocations. However, these dislocations have not been observed experimentally yet. So this is just a classification of dislocations in terms of velocity proposed by Whitman and also the subsequent researchers. Dislocation has very high acceleration. Acceleration is very high. I would write extremely high under most conditions. So the time interval and the distance required to bring the dislocation to a steady state velocity is very small. That means what is small? Or rather I should write r small. So the time interval and distance required to bring the dislocation to a steady state velocity is very small. So because the acceleration is very high and mostly these time required and distance can be neglected in most applications. Not all applications, but most applications. So this can be plotted in the x-axis, dislocation velocity small v divided by shear wave velocity capital Vs, and in the y-axis acceleration of dislocation. Okay, so this is in terms of 10 to the power 18 meter per second square, very very high value. So let's assume that 5, 10, 15 I would write here, and then 20. So and in this case we'll write this limit, this is 1 when the dislocation velocity will approach shear wave velocities. So here I would write these 0.8, 0.6, 0.4, 0.2, 0.2, that's a 0.4. So what will happen is, so there are two possibilities, we can have two approximations. One is a straight line like this, and the other one is at something like this. Okay, this may not be very perfect, but you just please check the Mark Mayer's the diagram. So there are two possibilities or approximations here. The first one, the straight line ends here around 0.5. So I would say this first one, this is curve number 1, let's say, and this is 2. So first one is considering only relativistic effects, and the second one, both relativistic effects plus damping, that is dragging mechanism, or simply we can write this as even damping. So this is the curve is for copper Cu, and then the damping coefficient B naught is 7 10 to the power minus 5 Newton second meter square, and the applied stress is 10 megapascal. So this is the information related to the plot, and initial acceleration you can see it's very high. It's from the plot you can see it is almost 2 into 10 to the power 19 meter per second square, very high value. So what will happen, we'll have both the curves. So we'll go to the next slide and we'll show you. So in the curve 1, this first curve, what happened is acceleration steadily decrease and becomes 0, and then if drag is present in the number 2, so what happens, the steady state velocity will be 0.5 times of that of the shear wave velocity at that applied stress level. So we have a 10 megapascal here. So I would just write for the curve 1, that is only relativistic effect. So the acceleration steadily decrease and becomes 0 when dislocation velocity is equal to Vs, the shear wave velocity, or it approaches the shear wave velocity. Number 2, if drag present, if we consider drag mechanism, the steady state velocity of the dislocation will be 0.5 times of Vs at the applied stress level. And also one important point, the steady state velocity in the case 2 is reached when the drag stress becomes equal to the applied stress. So this is drag stress and this is applied stress. If they become equal, the drag stress becomes equal to the applied stress, steady state velocity is reached. In any case, so whether it is case 1 or case curve 1 or curve 2, the acceleration to reach steady state velocity, that means acceleration of the dislocation, is very high. It's very high, and time required is very low. Very low. So for example, we just will give an example. For example, suppose the mean acceleration, in this case whatever we have seen in the earlier slide, that that from the curve, the mean acceleration, if it is 10 to the power 10 into 10 to the power 19 to the power 19 meter per second, and then the dislocation will reach steady state velocity in approximately 1.5 multiplied by 10 to the power minus 16 second. Very, very small time. So 1.5 10 to the power minus 16 second. So that means dislocations reach steady state velocity instantaneously. So with that, so we are closing for today. So we have discussed about the three mechanisms of dislocations motion. So first one is the thermally activated motion, and the second one is drag controlled mechanism, and the third one is relativistic effects at very high stress. This is all for today, and I think we will discuss a little bit of more about constitutive formulation at high strain rates, and then we'll go to the next chapter. Thank you.